All right, well, good morning, everybody, and welcome. I think we're ready to go ahead and get started. So today we're going to be talking about building HPC clusters as code in the almost infinite cloud. My name's Nathan. I lead a team of solution architects on the public sector side here at AWS, and I'm going to be joined shortly by my co-presenter, Gabriel, who's the HEP Cloud Facility Project Manager at Fermilab. So expectations for the session. We're going to talk a little bit about why customers are using AWS for HPC, leveraging Spot for big compute at low cost, and accelerating deployment with automated and managed services. Most of the talk is going to be around the infrastructure and operations side of deploying clusters rather than doing the compute work inside of them. So, quick agenda. I'm going to talk briefly about why AWS for HPC and some of the tools and techniques you can use to automate cluster deployment and make things faster and more agile. My co-presenter is going to talk about some of their successes, lessons learned, and some of the very cool things they do. And then we've got a really brief demo of one of the tools that you can take advantage of on the platform. So first, a little bit of nomenclature. There's a couple of terms here. HPC becomes kind of an overloaded term, right? That becomes a blanket for a few things, but there's actually a couple different types of workloads we'll talk about. On the left is HPC, sometimes called cluster computing. These workloads tend to be characterized by workloads that have more internode communication. So they're sensitive to latency. They tend to use larger instances and take advantage of features to control latency on the platform, like using placement groups to optimize networking. They also tend to use a smaller number of larger instance sizes. And sometimes we'll split the workload and run multiple clusters to kind of try to parallelize it and take advantage of the horizontal scaling. On the right, we have HTC workloads, high throughput computing, sometimes called grid computing. HTC workloads are characterized by less internode communication, so sometimes you'll hear them called pleasingly parallel. They can often take advantage of multiple different instance sizes, which can become important for leveraging Spot, and they tend to scale out horizontally very well, which makes them an excellent fit for the platform to be able to take advantage of our scale. So briefly, why AWS for HPC? What are some reasons customers are moving their HPC and HTC workloads to AWS? First is time to research. So HPC and HTC jobs tend to be ephemeral. You take a data set, you run a set of calculations, you get results, maybe you go back and modify your parameters and rerun, maybe you go gather more experimental data. But what that means is the jobs are bursty and often unpredictable. Central IT's goal in many organizations is to maximize the utilization of the cluster. This graph looks great when you own the cluster and you have to justify that it's being used and that that investment is paying off for whoever bought it, your research organization or your business. 100% utilization means no wasted capacity, right? But what ends up happening is, in many organizations, the job queue becomes the buffer. And this graph represents human behavior, not necessarily the performance of an actual job scheduling algorithm. But the idea is for a lot of organizations, the jobs build up because the cluster's scheduled, and you're just going to have to wait until the cluster's free to run your job. But in the cloud environment, we can work around this issue, right? In the cloud environment, you pay for what you use, and you can just request more resources. So you can run jobs faster because, like, from a compute perspective, you pay for EC2 instances by the hour. So 10,000 instances for an hour or 1,000 instances for 10 hours, it's the same price for the compute. So if your job scales horizontally, you can just scale out and run it faster. Or run multiple jobs in parallel. There's not necessarily a penalty for doing that. You don't have to wait in line anymore. And at the end of the day, when the jobs are done, you terminate those resources and don't pay for them. Nobody has to justify a very expensive cluster that's sitting idle. So another reason is innovation and performance. So a lot of these clusters and grids, this hardware is expensive. It's very expensive, big upfront capital investment. And the customers we talk to can't upgrade them very often. There's sort of the old joke that your computer is obsolete by the time you buy it and get it home from the store. But with the rate of advancement of compute technology, there's still some truth to that. So in AWS, we're constantly launching new features and products that you can get access to right away rather than having to wait till the hardware expires and rebuy new hardware that gets you the advantages of the new technology. Hopefully you all got to see the keynotes. Lots of new compute technologies released this week. F1 instance types with FPGAs, right? Elastic GPUs to be able to add GPU computing to instances. And those sorts of things are available now, and there were upgrades to a lot of the instance families that improve their performance. Another reason is scalability and flexibility. Once you've bought a cluster, if we're talking about a physical cluster in an organization, it can be difficult to reconfigure it. If you need to make it larger, if you need to resize the nodes, maybe you wish you had larger individual nodes, that can quickly become a procurement problem. If you need to configure the cluster for a different job type, a lot of organizations I talk to, that means literally wheeling racks around and recabling things to reconfigure the cluster for a different type of job in some cases. But in this environment, it's much easier to do that because you can take advantage of some of the automation we're going to talk about shortly to redeploy the cluster in the configuration you need. Need a small cluster? Deploy a small cluster. Need a large cluster? Deploy a large cluster. And my co-presenter is going to talk about some very large clusters or grids that they run to handle some of their compute workloads. Data becomes another reason that people are moving workloads to AWS. Now, that can seem counterintuitive. A lot of people say, well, taking advantage of the cloud computing, the hard part is I have to get my data there. Well, the good news is we have some services to help take care of that, right? On the screen here, we've got Snowball, ruggedized SAN appliance. That's the older Snowball. Of course, we released the new Snowball Edge, or announced the new Snowball Edge, rather. If you have data that you're moving back and forth frequently, Direct Connect can be a great solution for that. Dedicated low latency connectivity between you and AWS facilities to be able to move data back and forth reliably and quickly. And I don't want to forget and leave out Snowmobile, which was a pretty cool one the other day. But aside from having ways to move your data back and forth to AWS, once your data is in AWS, it becomes easier to share. So say if you're a public sector research organization and your data sets are useful to other organizations, you want to be able to share them. Once it's in AWS, it's very easy for you to do that. And in that vein, we have a lot of open data projects, we call them, that are data sets that are available freely on AWS for you to be able to use. So for example, the NOAA NEXRAD Doppler radar data sets and the 1,000 Genomes project, and there are many more that you can go look up that you can access today to run your own calculations on if you feel like it. So we talked about kind of a variety of ways that AWS can help save cost on HPC and HDC workloads. Paying for what you use versus having to pay upfront for hardware. Improving value by offering newer options and reducing time to results, right? Offering managed services that allow you to give up undifferentiated heavy lifting so you spend less of your time maintaining the cluster and more of your time hopefully doing research. And of course, 57 price reductions since 2006, I think we're up to with the most recent round over the last couple of weeks. So the cost of the platform continues to go down versus increasing like some platforms do. But when we talk about doing HPC and HDC workloads affordably, often we need to talk about spot. So the spot market allows customers to bid on unused EC2 capacity that's in the market. So spot works on market pricing. So the idea is you choose a bid price, and your bid price is the maximum that you'll ever pay for those resources. But what you actually pay is the market price. As long as your bid is higher than the market price, you get the instances you requested. If the market price goes above your bid, you get a 2-minute warning to shut down cleanly, and then we take those instances back. If you do get preempted, we don't charge you for the partial hour you ran. You only pay for full hours that you had use of the instances. So there's a lot of sessions on Spot. I'm going to give you a really quick rundown kind of visually here in this chart that to me makes it a little clearer than some of the ways it gets explained. So in this kind of basic example that we're doing with round numbers, there are 9 customers that have put in requests for Spot instances here. And they've put in various bid prices from $1 an hour all the way down to 5 cents an hour, which is a pretty widespread, but it makes an easy example. And then there's 5 of these instances, so it's per type per zone, so there's 5 of these instances available in whatever mythical zone that these users have put this request in. What'll happen is those bid prices will get sorted by bid price. If there's 5 instances available, the 5 will get allocated to the 5 highest bid prices. The market price becomes the cheapest one that got an instance, in this case, 20 cents an hour. So everybody pays 20 cents an hour. Even if you bid $1 an hour, you're going to pay 20 cents an hour because that's the going rate for the instance type. If another instance were to come available and get allocated to customer number 6, market price would go down to 18 cents an hour and everybody'd start paying 18 cents from there on. So to help you make intelligent decisions about how to come up with a bid for your spot instances, we released a tool a while back called Spot Bid Advisor. And actually, this is on the website. Anybody can get to this right now. You don't even have to have an account to go see the Spot Bid Advisor. And what it shows you is for a particular region and a particular OS type, you can see up at the top some of the selections we've made here to filter, it shows you what the kind of percentage chance of being outbid at a particular bid is. It works on the idea of a bid strategy where you bid a portion of the on-demand price. So in this example here, we said, all right, well, we're going to, if the on-demand price is $1, we're going to bid 50 cents, basically, setting 50% of the on-demand price. And it shows you in columns instance types that meet our filter criteria we set up there for the number of eCPUs and the amount of memory. The amount of savings you actually would have paid, calculated over, I believe, the last week, and the frequency of being outbid over the month and week, over the previous month and previous week, basically showing you how often over the last month would I have had some of my instances preempted. And you can see for the types up top, that was fairly low. For the types down below, there's more contention for those resources, so it'd be more frequent. For those, if you needed those specific types, you may want to choose a strategy where you go to 75% of on-demand or kind of whatever pricing makes sense for your organization. So getting more into the automation side of things, as promised, is Spot Fleet. So Spot Fleet is a way to build fleets of spot instances without having to put in a bunch of requests for individual types and individual zones. So the idea of Spot Fleet, and this becomes really good for grid computing type flavor workloads, is that you choose a metric on the types of instances. Some easy built-in ones are the amount of memory, the amount of CPU, whatever your particular workload's constrained on. Additionally, and what's shown in this example here is you can come up with your own weighting that's maybe set by actually benchmarking the instance types with your workload. You create a weighting for all of the instance types or use memory storage, whichever is most relevant. And you skip the slide, you want it. And then you set a target. So you can see in the second one down there, the target capacity for that fleet has been set for 100. So it's going to try to come up with 100 points of whatever metric you chose, whether that was memory CPUs or in this case, a custom weighting of different instance types for their actual performance on the actual workload. And it'll automatically schedule those resources. So a newer feature we released for this fairly recently is auto-scaling for Spot Fleet. So you can now also auto-scale a Spot Fleet and tell it to scale up using those same metrics and constraints you gave it based on, say, the size of a job queue or something like that, right, to be able to schedule more or less resources as time goes on. One other note I want to mention on Spot Fleet that I think makes it interesting, it has 2 kind of scheduling algorithms. One is designed for least cost. It'll favor whatever spot instance prices are the cheapest relative to your weighting. The other is that it can try to distribute them across all of the valid types. So you might want to use the least cost if least cost is your priority. But if you're looking for more stability and predictability, you can ask it to schedule across a lot of different types of instances so that if there's a spike in the market price of a particular type of instance, it'll have less of an effect on your total workload. So getting into the topic of the talk, we're going to talk a little bit about clusters as code. So we've talked a lot about why AWS is great for HPC and HTC type workloads. But a lot of that value depends on taking advantage of automation. So when we talk about the ability to resize your cluster, well, that means redeploying your cluster, which means to really do that effectively, you need to be able to automate it so that you can do it rapidly, right? These aren't things that you probably want to be doing manually on a large scale. Or you're going to be wasting a lot of effort. So the good news is that as hopefully you know after being here for a week, right? AWS is really designed for automation. Everything in AWS is an API. Everything becomes available in an automated fashion to you, or most things become available in an automated fashion to you. So now we're going to talk about some different types of automation that are available you can take advantage of, and I'm not going to read the bullet points to you about where we're going, but and we'll start from kind of the bottom, more custom options where you're going to build your own automation using our APIs, up to the higher levels of automation where maybe going all the way to the point where you want to manage service where you don't have to do anything. You can just enter your data transforms and requirements. So at the very bottom, the kind of most basic level is our APIs. Almost all of our services have an API, and the easiest way to access those is through our set of SDKs, popular languages like Python, .NET, Ruby. In the bottom right corner, additionally, you can take advantage of, if you're a shell junkie, you can take advantage of the CLI tools and handle it that way. And some plugins from some popular IDE tools kind of in the bottom center there that you can take advantage of. So heading up a level from using the APIs and the SDKs, you've got CloudFormation. So CloudFormation is a tool that lets you create templates that describe AWS infrastructure that CloudFormation will deploy on your behalf. This is really where the idea of infrastructure as code came from and where we use that term most frequently. So with CloudFormation, you create a template, you describe resources, and you tell it to create them. The example I've got on screen here is actually, a test one in the top layer, and the bottom one is a little demo I put together that creates a enterprise networking underlay, a VPC, some subnets to meet, say, maybe an organization's requirement for network topology. And here's a little bit of a look, if you haven't messed with it, of what a CloudFormation template looks like. Actually, fairly recently, a little bit before the conference, we released an update to CloudFormation that a lot of customers asked us for, which was support for YAML templates. By default, for years, CloudFormation did JSON templates. Some users didn't like those, preferred YAML, wanted easier commenting. So now we support YAML. We also have added support for cross-stack references. Which make it easier to do. Like a common pattern I see with a lot of customers is saying, well, I want to do, like in that last slide, I want to create a base template that describes a mandatory networking thing. Maybe central IT says the network needs to look like this and it needs to have these firewalls here and that sort of thing. And then I want to be able to create additional templates that I run on top of that schedule other resources to sit on top of that network, or kind of a base stack. Cross-stack references allow you to expose outputs from one stack and use them as inputs to the other, so you can effectively stack stacks on top of one another to be able to do those kinds of architectures. So next we'll talk about EMR, Elastic MapReduce. EMR is kind of unfortunately named because it's not just MapReduce. What it really is it's the Hadoop ecosystem as a managed service. So EMR has support for tools like Spark, tools like Hive, tools like Pig that a lot of you may be using for some of your data processing today. Monitoring tools like Ganglia built in. You can actually see some of the options that are built here in this just quick demo cluster I threw together to get a good screenshot for you, show you what it looks like. So if your workload fits something that can be done in Hadoop, EMR can be a great way to take advantage of that without having to actually do the hard part of managing a Hadoop cluster yourself. So announced earlier this week is AWS Batch. I'm not going to spend a lot of time on it, but just really quickly to describe what it does to you, or does for you. AWS Batch lets you configure jobs in job queues, right, your compute jobs. It acts as the job scheduler, and it also provisions the infrastructure on your behalf. So you can create jobs, you can create multiple job queues, you can set priorities on those queues, and you can send them out to execute on, say, EC2 spot instances, for an example. So another tool that's been around for a while, this is actually a software, open source software we offer, is called CFN Cluster. CFN Cluster, the CFN part's short for CloudFormation, right? So what CFN Cluster does is it uses CloudFormation to roll out a couple of common types of cluster architectures from the command line. And it's actually a Python tool that's available out of GitHub, and we're going to demo this a little bit later, show you how quick it is to throw together a basic cluster and schedule a basic job with CFN Cluster. Another popular product that we see a lot of customers use is Alsys Flight. So Alsys Flight is a partner product that's available in Marketplace. It is, you launch effectively the master node for Marketplace, and then it goes out and schedules the compute nodes. Part of why I think it's popular, one, it's offered at no cost. Alsys does paid support options, but they offer this for free to use out of the Marketplace. The other side is it comes preloaded with a lot of popular scientific applications that users enjoy, not having to go install them themselves. So that may be an option for you as well. And finally, as we get to the top, in our partner ecosystem, there's a lot of great HPC partners. Some of the ones on the slide here offer software products to help you do HPC and HTC type workloads on AWS. Some of them are actually managed partners that run on AWS, but they offer a more managed experience where you don't have to run the infrastructure, they'll handle it for you. And with that, I'm going to get out of the way and let my co-presenter talk about some of the cool work they're doing.
So I'll talk about some of the services that we have used from the list that Nathan has discussed before at the Fermi National Accelerator Laboratory. What we do, we run scientific workflows for high energy physics. The laboratory is the leading particle physics laboratory in the US, and it's funded by the Department of Energy. We have about 100 petabytes of data on tape, and our computing is following the paradigm of house throughput computing that Nathan was describing before. And essentially, we have two types of application. One is data analysis, where we have data in files, and an application runs for 5 to 24 hours and produces something else. Or we have Monte Carlo generation, so we simulate particles that come out of our detectors and produce some output, and so those also run 5 to 24 hours typically. We have strong collaborations with international laboratories such as CERN, and the Large Hadron Collider was in the spotlight in 2012. You might remember the discovery of the Higgs boson, and in 2013 we got the Nobel Prize for that. And Fermilab is the leading institution for one of the two experiments running there, one of actually 4 running there, and it's the compact muon solenoid, or CMS. Why are we evolving our infrastructure? Well, if you look at the top left graph, you have a measure, or a visual representation of the performance of the LHC, the Large Hadron Collider, over the years. And while we are in this, let's see, no, this doesn't work. Well, while we are in the, of course, 2015 to 2019 run, and we foresee to gather about 160 petabytes of data, well, when we go 10 years from now, we were asked to design a system to ingest 2 exabytes of data per year, which to me is very scary. And so how do we do this, right? We have to consider capacity, cost, and elasticity. And of course, when we then start to analyze these 2 exabytes of data that we gather every year, the analysis will not be steady state. It will follow peaks and valleys, like you see on the bottom right, that will follow holidays, conference schedules, et cetera, et cetera. So where do we go? And of course, the top right tells you that in order to do this cost effectively, the cloud may actually be the right solution for us. And in fact, the leaders of our field, this is what they recommend for us. They recommend, in fact, to start partnerships with industries. And this is what we started to do with Amazon. And we started to work on a project called the High Energy Physics Cloud, or HEP Cloud facility, which is a portal to a diverse set of back-end resources that allow us to scale to the needs of the community for pretty much all the workflows that are important. And of course, we have our architecture, but what's the basic idea is that we want to add resources from cloud, high-performance computers, grids, which are statically federated clusters, where we can share resources, or also local resources, into a central pool of resources. And as I mentioned, we are starting from Amazon, the leader in the market, to do this. But of course, when you start then doing the real work, then you realize that there are quite a few integration challenges. And I mentioned a few here, and in my talk, I will talk about these ones in more detail to give you an idea of what we had to face to integrate our scientific workflows. Well, the first one is how do we integrate provisioning? And as I mentioned, we want to create an overlay batch system. So you see our user on the top left that submits jobs to a scheduler. And then on the bottom, on the top left, there is what we call a front end. Let me see if I can use a pointer here. Yeah, so you see a front end here that looks at the number of jobs that are being submitted. And then, sorry, this is not, yeah, okay. And tells this component, which is also based on Condor, which is a batch system, to do the provisioning of resources based on the number that the front end has seen of jobs that have been submitted here. And of course, resources are provisioned at grid sites, local resources, high-performance computer, then of course, also clouds. And what is submitted to the cloud is a request to instantiate a virtual machine with a piece of Condor that will in fact report back to a central manager on the top right. And more and more resources will be accumulated there. And then with a matchmaking algorithm, the scheduling of the jobs to resources will be negotiated. Of course, you need to do this containing costs. And in this example, we ran about 3 million jobs for the CMS use case. And when you think about containing cost, Amazon provides a great way of doing that through the spot market that Nathan was discussing before. But you need to be sure that your workflows and your applications can actually sustain an interruption of service, so a preemption. In our case, the preemption was not too bad. We had 2.5 million jobs that were never preempted, but still, 400,000 were. And so the question is, what algorithm or what strategy do you use in your bidding to make sure that you minimize preemption and you optimize cost? And so at the time, we didn't have the spot advisor, the spot bid advisor. And so what we did was to, in fact, select on the bottom left a set of possible strategies from bid the minimum historically ever seen to bid on-demand price, to bid a fraction of on-demand price, to other more advanced and dynamic bidding strategies. And then we took the price history that Amazon provides, and we ran Monte Carlo analysis over them. So we say we have a 5-hour job. Suppose that we want to run this in a week. Can I actually find a window of time of 5 hours where my job finishes and doesn't need to restart all over again? What is the bidding strategy that optimizes my chance of success and minimizes my cost? And we did all the analysis, and in the end, for us, it turns out that bidding at 25% of on-demand is the best solution, rather than even being more adaptive or dynamic with the bidding strategy. And then, of course, you have to think, okay, but I'm used to running at local resources or at my clusters of friends at universities and other laboratories, but is the performance of the application really the same? And so what we did was running benchmarks on the various types of machines to try to select a number of machine types that, in fact, were similar in performance to the ones that we were used to. And on the left, we ran a benchmark that simulated particles, top and anti-top particles, which is very similar to what then we would be doing. And on the right, we were doing some other type of benchmarks. And in the end, there is a range of types of resources that meet our needs, and this is very important because in order to reach high scale, you have to bid on all different markets. So if we found that only a few resource types were actually performant, then we wouldn't have been able to reach the scale of 60,000 cores like we did later on. And of course, then we did also the benchmarks of data ingress and egress for S3. In fact, later on, we reached 12 gigabit per second of connection to our cloud. So then we ran these 3 million jobs, and we could do a histogram of the time that the application took to run. And we did that on a resource type by resource type basis. And so the peak there is about 4 to 5 hours. And this is a very good plot that tells us that the performance of the resource types at Amazon, is consistent. So we don't see anything, for example, on the right? So all of our applications more or less finish within 4 hours. Some are actually faster; they finish before. And this is a great consistency that is offered to us by Amazon. Now, the width of the distribution has more to do with the fact that these are Monte Carlo applications, and so each one starts with a different seed and produce different results, rather than the variation in time of performance of the actual instances, although the two effects are convoluted. But this gave us a lot of confidence that this is a good direction for us. Now, of course, we need to be able to be secure on the cloud. And we use the same baseline configuration that we use for our on-site resources. And so we've developed a mechanism to take what we call a worker node configuration and then package it in an HBM virtualization format and send it to Amazon so that the same security controls that we have locally also apply on the cloud. And this is now automated so that if we change the baseline, we can actually very quickly import a new golden image to Amazon. The other thing that is very important to consider is that we run hundreds of jobs, and in fact thousands of jobs on the cloud, and these do not run in a vacuum. They depend on other services in order to run. And one of the services that we depend on is in fact data distribution for software and for calibration constants, which we implement using a web data caching system based on Squid. So the idea is that we have software repositories at Fermilab, Brookhaven, other laboratories around the country. And when the application starts on the grid, or in fact on the cloud, it talks to a local Squid server that then redirects to Fermilab to get software. And then the software is cached at the servers, at the Squid servers, and then at the machines, so that then the ramp up is very quick, and we have very good scalability with this. However, when you run 60,000 jobs at the same time, you need about 60 hefty machines to run the Squid servers in our case. And you don't want to run these hefty machines 24/7 if you only run a few jobs and you ramp down and then you ramp up and then you ramp down. So the way we did this was using auto-scaling and deploying the whole infrastructure with CloudFormation, which is what Nathan was discussing before. And so what we did, we had Squid servers that were part of an auto-scaling group. Of course, we had them in different availability zones. And the auto-scaling group was ramping up the number of instances of Squids depending on metrics that were defined in the CloudWatch. And in this case, for example, we were ramping up when the aggregate amount of network traffic from the Squid servers was above a certain threshold. So that as we were instantiating more jobs, we could have more and more Squid instantiated. However, the jobs were always talking to the same elastic load balancer to talk to the Squid backends, and in fact, they were talking to it through Route 53. What the jobs had to do were essentially knowing what availability zone they were in, and then using Route 53, they would talk to the load balancer and to one of the Squid servers, depending on how many we had. Now, of course, we run these jobs, but we need the ability of moving the data. So as I said, we are expecting to have 160 petabytes in 5 years, and then exabytes in 10 years. We use the Energy Science Network, which connects Fermilab at 130 gigabits to the rest of the network. It's a network for science, for non-classified research, and it's funded by the Department of Energy. And ESNet has 3 peering points with Amazon. And in fact, when we started this in 2014, one was recently upgraded to a 100 gigabit connection. And this is why we could then easily get 12 plus gigabit per second of data ingress and egress. And to keep this cost effective for us, Amazon has introduced the concept of a data egress waiver. So Amazon, of course, charges for data egress because they pay internet providers, and of course, somehow the cost needs to be recuperated. So in our case, the network is paid for by the Department of Energy, so Amazon doesn't need to make a profit on us. And so they have decided to pass the discount on us and give us up to a 15% of discount where the transfer charges are at or below the 15% of the total cost. And this really makes it cost effective for us. And so when we think of data movement and data storage, then we can employ a couple of strategies to actually move the data back. One strategy is on the top right cartoon, and is, well, you have jobs that run, they analyze data, or in this case, they are Monte Carlo, so they produce some data, and then they want to transfer the data back to local storage. Fermilab has custodial responsibility of the data, so we must transfer the data back. Now, there is only so much that the storage elements at Fermilab can take. So if we run hundreds of thousands or tens of thousands of nodes, some will probably have to wait in queue until all the data has been transferred for the other jobs. So what happens there? You have virtual machines that are in a queue to transfer data, and you pay for the virtual machines. On the other hand, on the bottom right, you have a different strategy. You have a lot of jobs that are ready to store the data. You can use the highly parallel architecture of S3 to store the data all at the same time, and then later on, asynchronously, you can transfer the data from S3 all the way back, tuning your bandwidth to whatever you have. Now, in this case, though, you pay for the data in S3. Right? So there is a sweet spot that depends actually on the number of jobs and the bandwidth that you have between S3 and your site. And in fact, for one of our customers, CMS, we did the top right, and for another one, a neutrino experiment called NOVA, we did the bottom right. And then, of course, you need to monitor. We have integrated our monitoring solutions that our experimenters are used to with the Amazon infrastructure, so that we have systems based on Grafana that can show what's going on the overall system that we have, grids, cloud, and HPCs. And then we have accounting that also gives us an idea of the cost of the various instances that we have. Now, the use cases that we had, I mentioned two. We had 3 use cases. So on the top left, we had what we call a neutrino experiments. Studies one of the particles that we study, a very elusive particle called neutrino, which interacts very rarely with matter. On the bottom, we had CMS that I talked about a lot. This was the Monte Carlo simulation of events. And then we had another one. Now, this was also, this is an experiment that is associated with LIGO that recently discovered gravitational waves. You probably have heard in the news. And this is, again, another use case that tries to identify a signal from the sky and correlate the signal from the gravitational wave detectors, so that then everybody can observe that point of the sky, that region of the sky, and try to correlate the signal from the gravitational waves with the signal from the electromagnetic signature that we have from the supernova or whatever the event was. Now, I'll be talking about the bottom one, which is the one where we achieved the highest scale. And this is a picture of the detector. This is at CERN in Geneva. And well, you can see the scale. When we do simulation of this, we need to simulate particles that run through the detector. And how would the detector see this particle? And you have some visual representation, some event display, so-called, at the bottom. I said we ran about 3 million jobs for a total of 15 million hours. And the throughput, or what we call the bedput, which includes the preemption, was maybe less than 10%. So less than 10% of our jobs were in the end, of our total computation was affected by the preemption, which again was due to all the studies we had done on the bidding strategies, et cetera, et cetera. And this is, if you want, the victory plot. It shows that after we started our initial phases of tests, we could go and ramp up to, in fact, about 58,000 slots. And on the bottom, you see that we instantiated 10,000 VMs. Now, all the colors are the different resource types that we have used in Amazon. And the fact that we were really bidding on all these different markets was the key for us to be able to achieve that scale. Without being able to bid on all of the markets, you wouldn't have been able to achieve 60,000 cores. And then, of course, you can start looking at these trends a bit more in detail. If you look from February 1st, we were a bit more stable, and we were bidding always at the same amount. And so the peaks and valleys are really reaction of the market to the bidding. So you see that there are trends day after day of different types of bidding that happen in the spot market, and we are affected since we always bid at the same amount. We will have more resources or less resources depending on the market. And if you look at February 7, it was the weekend. Around that time, you see that it becomes flatter. So probably the big companies or the big financial companies were not bidding that much on the spot market at that point. Or at least this is our interpretation. Now, the impact that this had on our community was huge. So we could see an increase of 25% of the global capacity of CMS computing, as you can see on the left, by running on Amazon. And if you look at the number of jobs that were actually done, it's a huge peak on top of all the resources that we actually have, which is of the order of 200,000 cores. Now, costs. So we did a cost comparison between on-premises and the cloud. And you see the pie chart is our breakdown of costs. And this includes, of course, the cost of the node with some amortization, power, network, the salaries, which is a big part. And when you sum it up, we get to about 1 cent or slightly less per core hour. However, this assumes 100% utilization, which is never the case, because when you have I/O, you don't use the resource 100%. You have maybe a 90%, 85% of the utilization, which is what Nathan was talking about before. So if we compare this cost with what we got on Amazon, which was 1.4 cents per core hour, and in the case of Nova, which had a larger memory footprint, so they had higher virtual machine requirements, it was 3 cents. But so if we compare the 1 cent and consider that the utilization, in fact, may be 90%, that is very, very close to the 1.4 cents that we could actually achieve. The benchmark showed that, in fact, the performance is essentially the same. So our ability to provision 60,000 cores in maybe 1 hour is at a cost that is essentially the same, is really key for us to start bursting on resources such as the cloud and fulfill the needs of our community. And of course, I mean, we didn't do this in isolation. We thank Amazon and all sorts of other stakeholders and collaborators here. So with this, I terminate my part and I pass it back to Nathan.
So really brief demo we're going to run through here. So we're going to demo, or I'm going to demo, the CFN cluster tool that we talked about earlier. Like I said, there's a lot. I think this one is one that was interesting to me. This is going to be what I like to call a cooking show demo. So the whole deployment that I'm going to show here in the video, I'll start here in just a second, was about 22 minutes, I think, grand total to actually being able to kind of deploy a small cluster and do a hello world with all the automation, starting from scratch, including installing the software tool, right? The whole kind of run through it. What I've done is condense that down into about a 4.5-minute speed run. So no, I don't actually type this fast. But we'll go ahead and run it, and I'll narrate for you. So this is a Python tool. We're going to start with a clean Python environment and install it from scratch, and I'm going to pick the right version of Python. Again. You can install it through pip. You can install it through easy install. For folks that work with Python, those are pretty standard tools to install Python packages. It's also available on GitHub, our AWS Labs GitHub. It's going to install some packages and some dependencies, and we're going to run a quick built-in configure. I skipped over access key and secret key because those are already in my environmental variables. I picked a region, picked a SSH key, picked a VPC. That's actually just the default VPC in my account. Pick a subnet. I just randomly picked one of the 4. And the configuration part's done. So what we'll do is we'll go edit that config file. When you run that configuration through the tool, it actually puts a config file in your home directory. And we can look at some of the options that are built into that configuration file, VPC settings, et cetera. The configuration is an easy way to get started. You can go very deep in the configuration file if you want to specify details. And we ship with the package in the longest URL ever, an example configuration file that shows you what a lot of the options are. These are also available in the documentation, so you can see things where you can like specify some of the security group rules you may want or other security parameters for the cluster. And now we'll go back and we'll hit create. So I mentioned before, CFN cluster is kind of named for CFN as sometimes our abbreviation for CloudFormation. CloudFormation creates resources based on templates on your behalf. CFN cluster uses a CloudFormation template, but it also uses some extra services around that to help monitor it and deploy it. And it uses this command line tool so that you don't have to so with CloudFormation, you can enter parameters on a template. You can parameterize things like how many nodes you want, et cetera. This has a lot of parameters, so what's really been done here is to schedule some of the other things outside the template and to schedule some of the parameters on your behalf. We're using the Python script that wraps around it that makes that a little bit easier to get started so you don't have to mess with the raw CloudFormation script. And it's going to go ahead and run. So this portion, to give you a real sense of time here, took probably about 15 minutes or so to execute before it was finished. I, of course, condensed it down to about a minute for demo. So cluster's launched, nodes are launched. I'm going to copy out that IP and let's SSH to our master node. Don't steal my key. So here's our master node. So for the sake of demonstration, I'm going to schedule a really simple job. Let's just create a shell script that we'll use as our job. I'm going to paste in 3 beautiful lines, just wait 30 seconds and print a hello world with the host name of the node that executed. And we will submit it to the queue. And there's a couple of different scheduling engines that are available. By default, it's SGE, so that's what I'm using here. And it's been submitted, and we'll wait a couple of seconds and do a queue stat, and we'll see that it's running one lonely slot. And we will wait not quite a full 30 seconds because I condensed this a little bit more, and we'll see our output. Probably could have saved a couple seconds here. Queue's empty, job's finished, and I will very slowly type out the name of the output file, and we'll look at our output. There we go. Hello world from our execution node. And I didn't show it here, but basically to tear down the cluster is simply cfn cluster delete, I believe. And it'll tear the whole thing back down, shut it down, and you're finished. So, faked you out. So, nope, that was all. Thank you. I'm going to jump off stage. We'll hang out in the back or out in the hallway if anybody's got questions. And thanks for all coming out so late on the last day of the conference.